In this video we're going to focus on how to derive inequalities using the Hermite-Hadamard inequality. What is this inequality? This inequality is of the following form. So assuming that f is a convex function, then this inequality holds. The function evaluated at the a plus b over 2 is less than 1 over b over a, 1 over b minus a, times the integral from a to b of the function. And this is bounded by the sum of the functions evaluated at a and b divided by 2. So it's taking the average of the two. Let's have a look at an example. Let's say we pick that a, the lower bound, is 0 and b is x, and x is strictly positive. Let's take this case. Let's define the function f of t to be e to the power of t plus t. Let's define this function. Let's evaluate the first derivative of the function, that's e to the power of t plus 1. The second derivative of the function is e to the power of t, is strictly positive. So my function f is a convex function. Now let's take these assumptions for a and b. So we will have f 0 plus x over 2 less than or equal to 1 over x integral 0x ft dt less than the sum, the average of the two values f of 0 plus f of x divided by 2. Let's call this, let's rewrite this inequality as f x over 2. Then you have this integral times the reciprocal function. And then you have f0 plus fx divided by 2. Let's call this part little m. Let's call the term in the middle I. And this big M. So f of x over 2 is going to be, I'm going to replace x over 2 here in the function here. So it's going to be e to the power of x over 2 plus x over 2. That's the little m. Let's compute the integral I, the term I, 1 over x times the integral from 0 to x f of t dt. The integral of e to the power of t plus t dt. So that's e to the power of t 0x plus t squared over 2 0x. That's 1 over x times e to the power of x minus 1 plus x squared divided by 2. And now let's compute the upper bound of the inequality. M is the average of these two values. F of 0 is going to be e to the power of 0 plus 0 plus the f of x e to the power of x plus x, and then divided by 2. So that is going to be e to the power of x plus 1 over 2. So we have that little m is bounded by I, and then this is bounded by capital M. So we have little m is e to the power of x over 2 plus x over 2 bounded by 1 over x e to the power of x minus 1 plus x squared over 2. And this is bounded by capital M e to the power of x plus 1 over 2. So I have proved this inequality for x greater than 0. So I have proved that this inequality using the Hermite-Hadamard inequality. Hermite and Hadamard were two French mathematicians. And this is the inequality that we have used. If you know that the function is convex, so convex means so a convex function, let's say a convex function looks like, the graph of a convex function looks like this. So it's concave upwards. The graph of the function of a convex function looks like this. So if we know that the function is convex, then we can employ this inequality, and we can derive inequality using this Hermite-Hadamard tool. It's a really important inequality for convex functions. Of course, you have to be careful the domain of the function. You have to choose the domain of the function and then pick the appropriate function. Make sure that it's convex, like we have showed here. And then you can use this, compute the lower and the upper bound and the middle term of the inequality and reach that conclusion here. If you plot the graph of the inequality, so if you plot this function mx, if you plot this function, then you will see that this function I of x is between mx, is between this function and between that function. And this function is below that one, and this function is below that one. That's an example. What I wanted to share with you is a very strong inequality in the literature. Hermite-Hadamard inequality is a really strong inequality, and it's used in convex analysis and convex geometry.